All right, so we are going to talk about a discrete logarithm problem, but the hardness or the interactability of this problem relies on the group, the algebraic group. So before talking discrete logarithm problem, we have to explain what a group is. So here's a little bit algebra about groups, rings, and fields. But if you're more interested, there are very nice abstract algebra books that you can go to. In this video, I will briefly mention some definitions, but I will also give some examples so that these mathematical definitions will be easier for us to understand. So let's give the definition first and give an example. So a group G in algebra is a set of elements together with a binary operation star on G that combines two elements in G and form a third element in G, satisfying the following group axioms. First one is associativity. So if you first apply the group operation on BC and then to A, this would be same as first applying the group operation to A, B, and then C. There should be an identity element E such that, when you use this identity element with the group operation, it always gives the result as the A. Also, we require inverses of every element. So every element must have an inverse. And in this respect, we say that B is an inverse of A if and only if A star B and B star A equals to the identity element. This is how we define the inverse element. So actually, there are very easy groups that you can come up with after this definition. Think about integers. And as the group operation, think about addition. So there's associativity because we can easily remove these parentheses, right? Because the addition is associative by definition of addition. There's an identity element in this group, and it is 0, because if you add 0 to any element, it becomes the element itself, right? As long as the element is an integer. Right? Inverse element, every element has an inverse in this group, because let A be an element in Z, then minus A is the inverse in this group, because A plus minus A always gives you the identity element 0. So a very simple group. And don't forget that a group is defined by a set of elements, but also an operation. Here I defined addition. Let's give an example where something is not a group. Think about Z star. By Z star, we mean Z minus the 0. So because we will talk about multiplicity and 0 doesn't have a, something divided by 0 is undefined. So this is why we eliminate 0 here. And as a group operation, we choose multiplication. Now let's see if this is a group. So there is associativity, yes, because A times B times C is the same as A times B times C. You can get rid of the parentheses, in other words. There is an identity element. One is the identity element because take any element in Z star, multiply it with 1, you will end up with the same element. So the identity is here. But we don't have inverse elements. Not every element A in Z star has an inverse, because in order to multiply A with something and obtain 1, this something should be 1 over A. But 1 over A most of the time is not an integer, so it is not in this set. So, Z star with multiplication is not a group. But as you can guess, this is a rational number. So if we think about rational numbers with multiplication, then this is a group, because now every element has an inverse. Okay, so a very basic definition, a group, but they are very useful. But the important thing is as follows. So far, I gave you examples of infinite groups, because here we talk about Z, which has infinite to many elements. Z star also, infinite to many elements, and Q star has infinite to many elements. Since we are going to represent digital data as group elements, we mostly focus on finite groups in cryptography instead of infinite groups, okay? So let's give an example to a finite group. In this respect, I consider Z4 with addition. So Z4 is the set of elements 0, 1, 2, 3. This is a group because, again, this is equivalent to this in modulo 4, right? We can get to the parentheses too. So here, since we are in Z4, our addition operation is addition modulo 4. Okay. There's the identity element 0, because a plus 0 is equivalent to a modulo 4. And also every element has an inverse. So now recall the definition of an inverse. Something, for instance, 3 is the inverse of 1, because when you add 3 to 1, it ends up with the identity element modulo 4. So similarly, 2 is the inverse of itself, and 1 is the inverse of 3, which is, of course, obvious, because if 3 is the inverse of 1, then 1 should be the inverse of 3, right? So this is a finite group. And actually, these are the things that are interesting to us in cryptography. But of course, Z4 is a very small group with only 4 elements. So we will be dealing with groups with larger sizes. And most of the time, we might prefer to have this number to be prime for some reason, which we will explain in the future. Again, Z4 star with the multiplication is not a group. Here is why. We cannot find an inverse element for all of them. For instance, think about 2. 2 does not have an inverse, because let's multiply 2 with every element. Multiply 2 with 1, it is 2. Multiply 2 with 2, modulo 4 is 0. But identity element is 1 in multiplication. So multiply 2 with anything you want in this set of elements, you do not end up with 1. So it doesn't have an inverse. But the main reason for this is as follows. As you can see, the greatest common divisor of 2 and 4, 2 is the element we want to find an inverse for, 4 is the modulus. So the greatest common divisor of these two numbers is different than 1. This actually prevents the 2 to have an inverse. So this leads to another idea. If we want this the greatest common divisor to be always 1, let's choose this number as a prime number. So this way, the greatest common divisor will always be 1. And for this reason, of course, I'm not proving it, but just saying it, we will have an inverse. So think about ZP star with the multiplication. This is a group when P is prime. So when P is prime, we define ZP star as follows. Elements starting from 1 to P minus 1. There is associativity. 1 is the identity element. And due to the above reasoning, every element A has an inverse B in this set, where you multiply A and B and end up with 1 modulo P. Okay. So this is just basic number theory, but of course, we don't go into the details of it. Just know that this is a group. This will be important because we will be creating fields with these sets. Okay. So before moving on to rings and fields, let's talk about the generator of a group. G is called the generator of the group G if every other element of the group may be obtained by repeatedly applying the group operation to G. Each element can be written as a power of G in multiplicative notation. Each element can be written as a multiple of G in additive notation. So I'm saying this because I give you examples of group with multiplication and also addition. So in addition, we use the notation as multiples. In multiplicative notation, we use the powers to represent elements. So let's look at an example. Let's consider the group Z7 star with multiplication. We are saying that 2 is not a generator of this group. Let's look at it. First power of 2 is 2. Second power of 2 is 4. Third power of 2 is 1 modulo 7. So if you continue this way, since you reach the identity element, the rest will not give you anything new. The fourth power of 2 will be 2 again, because we are multiplying 2 with 1 modulo 7. So we started with 2. calculated almost every power of it and realized that it only generates 3 elements, but there are 6 elements in this set, right? But here's an example where we find a generator. We claim that 3 is a generator of this group. Let's start. First power of 3 is 3, second power is 2, third power is 6, 4, 5, and 1. As you can see, we generated all of the 6 elements with 3. So this is actually means that the element 2 has order 3, and 3 has order 6, which is the same as the order of the group. And also know that 3 is not unique. Maybe there may be an other generator. So a group might have more than one generator. The important thing is that, I'm not here that important, but the order of an element actually always divides the order of the group, which is somewhat important in these areas, but not for this course. All right. Let's move on to rings and fields and complete these basic definitions. A group is said to be abelian if x star y equals to y star x. So in all of our previous examples, we use basic mathematical operations like addition and multiplication. So this was always the case so far. But of course, if you are defining this operation in a very different way, for instance, think about this as a matrix multiplication. So if you multiply two matrices x and y, the result sometimes different than multiplying y and x as a matrix. But as an integer, of course, these are always the same. But when they are the same, we call them a commutative group or abelian group. Okay, so for the rest of the part, we are interested in this kind of abelian groups. So let's move on to rings from groups. A ring R in algebra is a set of elements together with two binary operations. Here I'm going to represent it with addition and star, but you can also use multiplication. But we wanted to satisfy the following. So this set R should be an abelian group with respect to addition. So we have seen groups under addition. So think about this as them. But we now added another operation. So we are requesting more properties like associativity of this star as follows. But we also request distributive property for these two operations. So, A star B plus C, here you actually distribute A as in multiplication, and it should be the same as this answer. And similarly, this one. So here, as you can see, we are actually generalizing the definition of group by adding more properties and more operations. So here are basic examples. Zn with addition and multiplication are ring, or just consider integers with addition and multiplication, they are rings. So note that I said Z and multiplication was not a group, yes. But here when I added the multiplication, it became a ring because we don't require multiplicative inverses for this star operation in this definition, okay? This is why this is a ring. But when you also impose that condition and ask for them to be, a group both under addition or multiplication, this will lead us to another definition called field. A field is a set of F which is closed under two binary operations, plus and addition and multiplication. So we ask F to be an abelian group under addition and F star to be an abelian group under multiplication. Here's another example. ZB with respect to addition and multiplication is a field when P is prime, and we represent it with FP. Electrical engineers generally refer to call this GFP, which is short for Galois field P, which are the same thing as this one. So these are actually the only fields you can get with, you can either have, a field with ZP here with a prime, so prime many elements, or a power of it. So this leads us to the definition of finite fields. If Q is a prime power, by prime power, we are saying that actually power of a prime number, like, fifth power of 2 or 10th power of 3, these are prime powers. So if Q is a prime power, then there is essentially only one finite field of order Q, which is denoted by FQ. So you can only have fields, finite fields with fq, where q is either prime or power of f prime. So with these basic definitions, now we are ready to talk about elliptic curves, because as you can see, I tried to explain what a group is. In the case of elliptic curves, we will define a very different operation called addition. And there we will add the points on the elliptic curve and define a very different way of creating, we will define a very different group with respect to point addition. So instead of regular addition here, like integers, we are going to add points on an elliptic curve, and that will create a group. And discrete logarithm problem will be a lot harder in that group. So this was our roadmap since the beginning.